The part of the LT4. Parts and pieces.
We got one here too.
Here's some of the pistons. I guess there's all 8 they've gotten taken out so far. I mean, size comparison.
Performance Build Center, which is an engine assembly facility over inside the Corvette plant. This is Pedro, this is Reese. These are 2 engine builders. They're going to build this engine for us today. The Performance Build Center, if anybody was familiar, was a small plant up in Wixom until a couple of years ago. I've seen, probably some of you have heard of that. Back in 2013, they decided they were going to close that facility and move it down to Bowling Green. Wixom made the Z06 engine for the C6. They made the ZR1 engine. They made the CTSV engine, and I believe they made the ZL1 Camaro Supercharger engine also. So a lot of those engines went away, and it was a good lull in there to move that equipment down. So there was a small area. If you've taken the plant tour, you've seen the walled-off area inside the Corvette plant. We moved all that Wixom equipment down here, and we started in February of 2014. Started making the 7-liter LS7, same engine that used to go in the Z06, or a very similar engine, and that's been going in the Z28 Camaro since early last year. It's still going in the Z28. And in the fall of last year, in September, we started making the LT4, and this is the Z06 engine. Now, there's 2 engines that go in a Z06, or it's the same engine, but you can get an engine from 2 different places going in a Z06. If you order a standard Z06, you'll get an engine just like this, built in Tonawanda, which is where they make the LT1 base Corvette engine. We make the identical engine here, but you get ours if you order a Z07. So in addition to carbon fiber ceramic brakes and all the other Z07 goodies, you'll get a PVC engine. And we'll show you later. It's built by one person from start to finish. They attach the block to this cart, and we have a series of build stations. Now normally there's like 10 of these stations. We combine all that into one. So this thing is a big mess here. But in our assembly line, they will push the engine from station to station and put on certain parts of each station. So I just wanted to show this. This is part of our build process and how we error-proof the assembly and make sure all the torques are done correctly. We scan, when we go into a station, we scan this here. This piece of paper will be attached to the engine. That tells the station what engine's coming in. And then each station will have just one of these. So there's station one's sheet. And for each part we're going to torque down, you scan that. It tells the box what you're about to install, programs it for the correct torque, and looks for a certain number of rundowns. So you'll see we're going to hit, for example, on the cam retainer, there's 3 bolts. It'll look for 3 green lights, and it won't let you out of that. It won't let you stop doing that until you get 3 good ones. And this is how we ensure our quality process. It's part of our quality process. So you'll see us going back and forth. Now, normally when we're building an engine, these torques are all different, and a lot of them are quite high. We go over 100 on a lot of different 100 Newton meters on a lot of different fasteners. Today we're building this engine with entirely 10 to 15 Newton meters, just so it's quicker, number one, and we get it apart easier. And this engine's been apart, together and apart probably, I don't know, 20, 30 times. So you wouldn't want this one after you finish it at all.
Who gets that one?
Any questions before we get started?
The single builder just moves the engine from station
Yes.
to station to station.
This is an actual production cart, engine cart. They can do something identical to this. Push it around a bunch of stations, look just like that. So. And then we have some testing at the end, which I'll talk about when we get finished there. All right, so the first. look at my notes here. I don't want to forget anything. A lot of good stuff on this. First thing we're doing is camshaft is the first thing to go in the engine. Normally there's a assist tool that goes on the front end of it that helps you guide it in. They actually doing that. It's a good job, Pedro. We're not going to get
Thanks, Todd.
those on there. And normally we put a lot of assembly lube in the engine, so every part that goes in internally, you coat it in Lubazol, which is a kind of oil type pre-assembly lube. Doing that, avoiding that today for the mess. We don't want the mess.
You mentioned the tolerance of
I don't, you know, I couldn't tell you, like, talking like cylinder bore clearance and things like that. Unfortunately, we don't know, I guess I couldn't tell you all the design aspects, but they're pretty tight. There's not a lot of room in there. For emissions and for durability, you need to start out with pretty tight tolerances. So those cylinders are, you know, double honed, pretty fine finish. There's really no break-in period. So they're right at the correct diameter when we start. I wish I'd have. One of the features of the cam is there's an extra lobe on the cam. If you remember back in you guys that have had 60s and 70s engines apart, there was a lobe on there that drove the mechanical fuel pump. This has a lobe on there. It's a special lobe. It's three-sided, so it's a triangle. It's on the back of the engine, and it drives a mechanical fuel pump that's used for the direct injection, which I'll show you that when we get to it.
So it's kind of one guy puts the camshaft in, the next guy puts the crankshaft in, and just moves along.
Tonawanda is a traditional assembly line. Very high-tech assembly line compared to 20 years ago. I was in engine plant 20 years ago, and when I saw Tonawanda just recently, I was shocked how much things had changed. But yes, it's a moving assembly line and stationary operators. So opposite. We have the opposite concept. Reese is installing the squirters. This is a new part that was not on the Gen 4 V8. This is new for Gen 5. It's on the LT4 as well. These engines have AFM, active fuel management, which cutting down to 4 cylinders. When you're in 8-cylinder mode, with variable pressure oil pump also, which I'll show you. But when we're in 8-cylinder mode, the oil pump's putting out around 60 psi. This squirter has a check valve in it that only lets oil through when it's over somewhere between 40 and 50. So 8-cylinder mode, these things are squirting oil. They're positioned just below, basically at the bottom of the bore. They're shooting oil up into the bore, cooling the bottom of the piston, keeping the crown of the piston cool. When we're in AFM mode, 4-cylinder, the oil pressure drops to 40. These things stop squirting oil, so you don't need that cooling oil. It allows for more efficient operation. Not pumping so much oil.
You know, it's the same 4 cylinders that drop off.
It's the same 4 cylinders drop off. It's 1 and 7 on the left and 4 and 6 on the right. Those are either on or off.
And it doesn't cause extra work problems when you do that?
You know, people have asked that, and I mean, the same concept as a long track record in the trucks. They've been doing this for almost 5 years. They've been on the Gen 4 truck. I haven't heard anything like that, so I'm going to have to say no. It doesn't allow extended periods of 4-cylinder. After so many minutes, it will kick on back to 8-cylinder just to warm those cylinders back up. Obviously, if you ran for a half an hour, you know, cruising 4 cylinders, they get pretty cold, and the cylinder walls will dry out, and you have stress and things. So it does kick back into 8 periodically just to keep them warm. They're on the LT1 as well. Teresa's laying the crank now. See this little gear looking thing on the back that's not on the old style cranks. It's been on cranks for at least 20 years, but that's the reluctor ring. That has a series of teeth on it. And there's a sensor that goes in the side of the block right here that tells the ECM, engine control module, that tells the ECM where the engine is at all times. It detects misfires, it tells the ECM how fast the engine's turning. Those are the 2 main things it does. That's a forged steel crank. block is six main cap bolts per journal, 4 down and 2 in the sides. That's common. That's been common on the LS engines since the beginning. This block is actually the 6.2 block. It's actually the common block with the LT1 and some truck engines as well. So this is a good strong block. It's used on almost, well, basically all the 6.2s, small blocks. You'll see as we're grabbing parts, we're kind of grabbing them ad hoc from different places. The way the PVC works, to minimize confusion, we have a series of small tubs, what we call kits. They will have, let's say the first kit will have the squirters and some of the smaller parts in. The next kit will have the next set of parts. So that's how we, number one, make sure we get all the parts we need for the engine to the line and no more. And it minimizes just the clutter we have on the floor. We have pretty clean. Come out and look. We don't have a lot of material sitting on the floor. Most everything arrives to the line in kits.
Question here.
Sure.
If you want to do the engine build, so one of the techs will stay with you?
I'm glad you asked that. The engine build experience, to build your own engine. You can get, now this is the one way that you can get a regular Z06 and get a PVC engine in it. You can order the build your own standalone option. You get to come in, you get to work with them. We have 25 builders in our facility, so it'll be one of those 25, could be Pedro, Lisa, or one of the others. And they will let you do as much or as little as you want. You start out just like we did here with the bare block. And if you want to lay that crank in there, you can lay it. You can watch them lay it. You can do it. We've had people stand back and watch them build the entire engine. And then we've had guys that wanted to turn every screw. So we'll accommodate the whole range. I don't know if you've been watching Pedro as he gets ready to do each torque. We'll go scan the box and it'll, in this case, it's looking for 10 of those hits. And we'll let him stop doing that until he gets 10 of them.
Is there a specific pattern that you're following as far as the...
Well, talking about the multi.
Yes, there is, but we normally wouldn't use this. We use these guns a lot to build this engine. There's several places we use a multi-spindle setup where, obviously, ideally, you'd want to shoot all 4 of these at one time. You get the most uniform clamping, all this, everything would be synchronized and drawing the joint up square and tight all at the same time. These pairs are so tight you can't actually get 2 spindles right next to each other, so you can't get 4 motors in a row. So we have a variable distance tool that comes in and will shoot these 2 and spreads apart and shoots the outer 2, which gives us pretty much the same effect. So it gives you more uniform clamp load, less likely to move ever.
But basically you're attacking one cap at a time.
Yes. Yes. Yeah, we do inner outer.
Okay. Main caps first as well. There's mandatory sequence, yes.
Yeah.
Yeah, definitely.
Everything you'll be doing is build.
Yeah, so over here, you're not going to see us doing exactly how we do it at the plant.
Okay.
Obviously, like Todd said, you're not going to want this motor anyway. And a lot of the mandatory sequences, what we'll have is templates set up at each station.
Okay.
Because some of these mandatory sequences are quite long. Like Supercharger, you're going to have like 20 bolts or so. Head,
When you see him do this, there's a program pattern that you have to shoot these 20 bolts in.
Yeah, so to keep us from having to remember each sequence and getting it right every single time, we have a template there that ensures that we know what it is every time we're there. And it helps us out a lot. We're trying to make the job as easy on us as possible.
Now he's doing the sides. Those side bolts have a vibram seal, basically keep oil from leaking out, because these do get oil exposure to the outside. If they weren't sealed, they would get.
So you're saying this is similar to what would be in my SUV then? I have a 6.2 liter Escalade.
So what we've got here is kind of similar.
Okay.
while these, all right, I'm sorry about that. While these guys are they're getting ready to stuff pistons here, I'm going to set up a little PA system. I think it'll help the folks in the back. Hey, do you want to tell them about the pistons and rods while you're showing the rod bearings? The piston rod assembly comes to us assembled with the rings on it. It's a forged piston. Before they stuff each one, they'll rotate the rings, at least make sure all the gaps are at least 90 degrees apart. That tool she's using there is customized for this bore size and for this engine, so it's only good on this engine. This is pretty much the process we use online. Only one person would do it by themselves. Get a little help here, which makes it go quicker. Yeah, it's basically like a funnel. Let's see a plug over there.
Check, check. How's it in the back? All right. Sorry about that. So they basically start at one end of the engine and work to the other. As each, actually as they assemble the bearing caps to the rod, previous to the station, they would have put the bearings in the caps. There are, I don't even have one to show you at this point. But they would inspect the bearings. This bearing? These bearings are new for the Gen 5. Before this, you would have had a leaded, basically tri-metal bearing, similar to the thing we've had for years. I can turn this up just a little. As part of the European regulations and just general environmental friendliness, they're eliminating lead, so we've gone to a aluminum bearing with a polymer coating. It's similar to Teflon. It's some kind of proprietary formula that I can't get Federal Loma to tell me exactly what it is, but it's similar to Teflon. And one of the things we do that's some of the extra care we do a very thorough inspection of those bearings front and back before they go into the rods. Inspect the rod caps and the rods also. That little green tool there is just something that guides the big end of the rod over the crank so that you don't scratch the journal, and basically just makes it a whole lot easier. The rods are a powdered metal, rod that has a fractured cap. What that means is the cap and the rod are together originally. They're cast as one solid piece with a kind of a V-notch. Big hammer comes across and knocks that and breaks the cap off. So you've got two unique fingerprints, two snowflakes. There's no two alike. That cap is forever with that rod, and when they go together, they fit perfectly with a jagged interface, let's say, so that they can never move, and it's basically a bulletproof joint. After the pistons are all in and the rods are all tight, we do something called torque to turn, which is just like it sounds. A tool goes on the end of the engine and spins it, listens for noise, and measures the torque it takes to turn it. So if there's any foreign debris that happened to fall into one of the bearings as we were assembling them, if there was something wrong with one of the rods, if a piece of debris got in between a piston and the bore, all those things can be caught with a torque to turn. It doesn't happen very often. But that's just one of the ways we ensure that the clean assembly going together, it's not going to give us any problems. There'd be oil dripping all down the side of this engine right now normally. As you take each piston and get ready to put it in, you have a foam roller, you just coat it in assembly lube right before it goes into the funnel there. So yeah, there's oil everywhere when we're doing this normally. Boy, it's almost as many components as there are, really. We get the blocks and heads from Tonawanda Engine Plant, so they're actually made by GM. They make the blocks and heads for us, yep. I think, is there any other big supplier that makes multiple parts? Federal Mogul makes a couple things. They make the pistons, they make the front and rear covers. Pretty much every part has its own supplier almost. Yes?
What would be the total cycle time for one of these in production?
That's a great question. In an 8-hour shift, one builder makes 2.4 engines. So it divides down to 2-point-something hours per engine. We're obviously doing a quickie job here with not all the normal steps followed. They just put the cam chain guide on there. I don't believe so, no. They're not supplying any parts for us. They actually built the engine, the base engine for the C6. I don't think they're making anything for us now. Pedro's getting ready to put the timing set on. Now this is a lot different than a Gem 4 timing set. He's going to hold it up here. But this is the heart of the variable valve timing system. There is, basically this is what you call a phaser. And depending on how oil is directed into that, it can advance or retard the sprocket relative to the center hub. And that's how you get your advance and retard for your VVT. This is the control valve, and it's hydraulic. Basically, you have a little spring valve here on the end, and it is actuated by a solenoid that's in the front cover. But depending on how deep this is pressed, it sends oil to different passages, which will advance or retard the sprocket relative to the crank. I believe it's total amount of cam timing that we get is -7 and +15 56, I believe, or 54 crank degrees. Because we want this engine to run right when we fire it up. He's going to make sure he sets the timing correctly. You see number 1. We're not really going to fire this engine up. We're not going to do that. You want to show? I don't know if you can show them that. The question was, is there an alignment mark on the gear?
So we make sure it's lined up whenever we're installing. So we set the engine where we need to for correct timing. We have the cam locked in the correct position that we need to. Then we just make sure our gears are set up.
So is there, on the back side of that, is there something like around the camera rotation?
Yeah, there's actually a locating pin on the cam.
Okay.
It's going to fall into place right there.
Okay, thank you.
Yeah.
I don't know if anyone's built a Gen 4 here, but it hasn't pressed on. Crank sprocket, this one isn't. It basically slides on and slips in. This phaser valve is also a bolt. It's got a thread on it that retains the gear onto the cam. And it's one of the higher torque fasteners we have in the engine. It goes over 250 newton-meters quite often. It's a torque angle fastener. Tighten it to 80, and then it's, I believe it's 120 degrees more after you get to 80. So the final torque is usually in the mid-200s. Probably didn't see it, but she installed a thing called a widget on the back of the cam, basically that keeps the cam from turning while they're tightening this. One of our many assembly aids. Normally that tool is fixtured. You would not want to hold that with 250 newton meters on it. But that one only got 15.3 according to the box over there. Yes? That's a good question. Some of the fasteners do. The question was, do we use any Loctite on the fasteners, or is it just interference fit? Say somewhere around half the fasteners have a adhesive patch on them. All these are used up, so you don't see them. So let's say when this bolt was brand new, it would have had a blue or white patch of sealant on there. I think it's activated when you drive the screw in. A lot of times it's a 2-part formula that will get mixed when you drive the screw in. And some of them are Loctite and some of them are geared more towards sealant. But short answer, yes, a lot of them do have something on the threads. Oh, this is one of the key parts of the Gen 5 engine, which this is, and as part of the AFM system where you're disabling 4 cylinders, you want 2 different oil pressures. Remember, your high pressure in 8-cylinder mode is 60 plus, and in 4-cylinder mode, you're limited to around 40. Just kind of hold that up. So this pump, in addition to being 2 different output pressures, is actually 2 pumps in one. This engine is a dry sump engine. You don't have a big oil pan that holds 10 quarts of oil. Basically, you have a flat oil pan. All the extra oil is held up in the dry sump tank in your right fender. So this pump having 2 pumps in it, one of them is called the scavenger pump. It basically takes all the oil that drips down into the pan, sucks that up, and shoots it back to the tank. The pressure pump, these are basically stacked. Here's one, here's the other. The pressure pump supplies the oil to the engine. The pressure pump has 2 modes that are controlled with this solenoid. So we actually have a lead that runs inside the oil pan from the outside, passes through the front cover, connects there, and that commands either high or low pressure out of this pump. Yes? You know what? I have never looked to see. The question was, do you see the oil pressure change on your gauge when it goes into 4-cylinder mode? That's a great question. There's one of the guys back there that drives one every day. He says he's never seen it. I've heard the 4-cylinder on this engine is not as aggressive as it is on LT1. So on the base Corvette, you can tip into the throttle a little ways and you can climb actually slight grades in 4-cylinder mode. This one must come out easier and go back to 8-cylinder mode. This engine was not designed, I mean, you're getting the best economy you can out of 650 horsepower, but if you had to choose one or the other, the choice was always made for power on this engine. You want that on tap as soon as you ask for it. Yes, a lot of the bolts on this engine, I don't believe the oil pump bolts are. The question was, do we stretch the bolts when we installed them? A lot of the bolts included the main caps, the rods, the head bolts are torque to yield. So you turn it to a certain torque, which puts the parts together, and then you turn it another so many degrees. During that process, usually the bolt goes into what you call plastic deformation mode. You stretch it to a point where it's not going to spring back all the way. So you've actually deformed the bolt slightly. You can do that twice, and then you need a new bolt. So if we ever, for whatever reason, we need to back a bolt out and shoot it again, if we ever do it more than twice, it gets a new bolt. So a lot of the critical joints are torque to yield and torque angle fastening strategy, and you need a new bolt when you're putting the engine back together. Here's the front cover, a little bit more complicated than the old Gen 4 front cover. Here's the solenoid I was talking about that actuates the variable valve timing on the cam phaser. And we've got some extra harnesses on there, but this, from this side to this side is the pass-through that controls the 2-mode oil pump. The one other thing we do different on the Gen 5 versus the Gen 4 engine, there is no gasket on that cover. That is 100% RTV sealant. In our system, we have a robot where there's a holding fixture that goes into. The robot comes in and puts a very precise bead all the way around, and that's the permanent seal on the engine. So if you're ever pulling one of these apart one day, you'll be scraping a lot of RTV off to get that cleaned up. It's a pretty aggressive bond, so it's actually kind of difficult to get that cover off sometimes. Actually, on this engine, the front cover, the rear cover, and the oil pan all use the RTV silicone as sealant. There's no gaskets on any of the three. I'm going to show the oil pan real quick while they're doing the front and rear covers. This is a dry sump oil pan. This engine takes 11 quarts of oil, but you wouldn't know it by looking at this pan. Difficult to do here. The two hoses that go to the scavenge pump basically pumps the oil out. One of these hoses up to the fender tank, and returns back through the other one to the pressure pump. And here's where the oil pan mates up to the flanges on the bottom of the oil pump that we were looking at before. I have to trace it every time, but one of these is the pressure side and one is the scavenge side. So there's some hidden pipes under here also that pick up the oil from the sump. It comes to us with the filter on it. We have to be careful how we handle that, of course. We don't want to ding the filter up. And if you'll notice, there's two drain plugs in that thing. One of these drains the sump. And the other one drains one of them drains the pan itself. The other one drains the dry sump tank under the fender. So that is the one you really want to make sure you drain when you're doing an oil change. There could be anywhere up to 8+ quarts in the tank at any time, especially right after you shut the engine off. There's a lot of oil up in the tank. If you don't drain that, you think you're done with the oil change, you dump 11 quarts in, and you had 6 quarts left over from before, now you got 17 quarts in your engine. That never ends well. One of the next things we're going to put on is the oil cooler. This is a bigger oil cooler than the, and it comes with the bolts in it. Bigger oil cooler than the LT1. And it is a water to oil cooler just like that one is. We get water out of the side of the block. From this hole to basically circulates through here and keeps the oil down around at, at max at the coolant temperature. Now we do have a torque sequence on the oil pan. It's shot in our process very similar to what Pedro is doing there. So he has a pattern he runs back and forth on doing the oil pan. Now I said it was a couple of hours per engine for our builders to do them. If anybody ever does do a build your own, that's typically an all-day process. You come in the morning, you get just a little continental breakfast. We have a safety video to show you how to stay out of trouble on the plant floor. And we go out and start. You can spend, probably getting up to this point, you may get to this point about lunchtime, maybe a little further. We've had people that were at this point, we've had people that are almost done at this point in the day. So it's all depending on how fast you want to go, how much detail you want to get into. Typically we finish up around 1 to 2, and then you get to see the engine go through cold test, which is where it attaches to a large machine that spins the engine over, and we look for the amount of torque it takes to turn it. We listen for noises. There's microphones in there that listen for noises. We monitor the pressure pulses going in and out of the engine, into the intake, suction pulses on the intake, pressure pulses on the exhaust, all kind of diagnostics you're doing, cold test, basically checking all the functions of the engine. Yeah, Pedro's about to install this, call this the Mega Lifter. It's very similar to a regular lifter. It's got a roller on the bottom, it rides on that three-sided lobe that I talked about at the rear of the engine. This basically gives you an up and down action and drives our mechanical fuel pump. So that's a unique part to the Gen 5 and also LT1S. I bet it's probably the same part on the LT1. So after cold test, when you're doing your build your own engine, and all engines get these tests as well. If it's a manual, we'll go to balance. And actually, we'll show that when we get to the flywheel, but the manual engines, mainly because the main reason is your hand rests on the shifter. If there's any small imbalance in the engine, you feel that vibrating because the engine's fastened directly to the torque tube. Shifters bolted right to the torque tube. So in order to keep those vibrations down, we do a fine end balance on the manuals, getting it down to half an inch ounce, within half an inch ounce of end balance. These are the regular lifters. These actuate the push rods, which actuate the valves. They are standard roller lifter on these two, and the hold the engine lift right. I thought they were losing. Okay. Here's a regular lifter. There's basically that's been the same since probably the 90s. Very similar lifter has been used in all the small blocks all these years. This guy keeps them square, keeps them from rotating, so it keeps the roller going in the direction of the cam. The AFM lifters, basically there's some extra stuff in there, and it's retained in there pretty well. It's hard to get out, but it's basically that tall. It's got some extra oil passages in it that allow the inner half of the lifter to unhook from the outer half. So the roller will still be going up and down, but the push rod won't be moving. It's basically allows the lifter to accordion, let's say, and that's what shuts off those cylinders during the 4-cylinder mode. Basically keeping both valves shut so that basically the compressed air in that cylinder acts as a spring. You put energy in as you're compressing the air and you get it back out on the way down. And there's always one cylinder going up and one cylinder going down, so it all balances out to be net zero. Doesn't put any drag on the engine. Now they're putting the head gaskets onto the block. It's a lot of you came up and saw this before the build. The head gasket has 7 layers in it. It's basically a super high, heavy-duty design. This engine is 10-to-1 mechanical compression plus up to 9.4 pounds of supercharger boost. So as you can imagine, the cylinder pressures in this are, I don't know if they're double, but they're a lot higher than a normally aspirated engine. The head is about to sit on there. We get from Ton 1 engine plant again. It is a unique head to the LT4. It's made by, casting is special, and it's a process called roto casting. They do something where they, I don't know if they spin it, but it results in a much smoother casting, less porosity, stronger, less expansion issues, porosity issues. So it's a more expensive casting to begin with. The intake valve is solid titanium. The exhaust valves are sodium filled. And the intake valve being titanium, they have a, we can show that at those caps on. You can see the intakes have an extra little, it's a steel cap right on the end of there. Titanium doesn't wear so well, so that gives us a better wear surface on the titanium intakes. That's another item that we have a series of checks in place to make sure those are all on there. All they are just sitting on the end of the valve. They will come off really easy. We got 10 head bolts, and these would normally be run down with a 10-spindle tool that does all 10 of them simultaneously to get a very even clamp load across the surface of that gasket. Next part that's going to go on is affectionately called a Loma. It's a lifter oil manifold assembly. This is a very high-tech looking thing. All it does is turn on and off the AFM system. It gets oil fed in here, and it controls, with some solenoids, it controls the oil going down to the 4 sets of AFM lifters. And it rotates it up, I can show you the holes. But these oil feed holes are the ones that control the AFM lifters. And this basically shuts off the oil to them, as well as providing a cover for the valley area. Normally on the Gen 4 engine, this was just a flat plate that covered basically the valley cover. This has a connection for the actuation of the cylinders. Also has an oil. This is a PCV fitting, vacuum supply there, and this is the oil pressure sensor hole. We take oil pressure there for the engine. This is one of the times where it takes actually longer here to do it than it does in our process. We 10 and done all at one time normally. Teresa's putting the Loma on and they're going to shoot. Now that one we do assemble with an individual wrench normally. So she does that one we would. Last but not least, this is the third part of the Gen 5 V8 that is basically a major change and improvement from the Gen 4. This is the mechanical fuel pump. This again rides off that mega lifter, which is actuated by that three-sided cam on the back of the camshaft. Basically, we need pressures in the direct injection system to reach up to 2,900 psi. So there's basically no way to achieve that with an electric pump. You need a mechanical pump for that. And this is it. This has a connector on the back where the ECM is controlling the fuel pressure in real time, depending on the engine demand and speed. Now, if you can imagine having 2,900 psi gasoline on top of your engine, that's something you need to make sure that doesn't get out, doesn't get loose from there. So we are getting ready to install some of the high pressure fuel lines. Actually, we're gonna do that after the rocker. Sorry, getting ahead of them here. Fuel pump goes on, and then we finish up the valve train, which is our push rods and rockers. This will take a little while here with the two of them working together. One person alone, this is one of the longer steps of the assembly process. Yes. The question is there a break-in process? They're always going to recommend 500-mile, not holding steady speeds, and that's mainly for the rear end differential brakes, things like that. The engine is pretty well broken when you put it together. The hone on the cylinder walls is a fine finish. The bore size is tolerances are precise. the bearings are precise. So short answer, not really. This engine does not need a break-in. Now, one thing that does need broken, if you looked at the, I don't want to pick this thing up, it weighs 60 pounds, it's more than one hand, but if you look at the rotors, they do have a black coating on them, and that is a sacrificial wear coating. So these rotors are actually assembled together. They need, as you can imagine, they're basically just two helixes that are interlocked together. So if you're going to compress air with that, you need extremely small tolerances, small gaps in there. So what they do is they actually fit these together tighter than you would normally, but you have that sacrificial layer on there. So this can, you may get a little extra noise out of this in the first 50 to 100, couple hundred miles, as that sacrificial wear layer works together and perfects the fit between the two rotors. I would say this is the only thing I'm aware of on the entire engine that would be break-in, but you don't need to necessarily take it easy on this. It's a dry system. It doesn't have, it's not lubed or anything, so it's really just time and revolutions it needs to wear itself together. Sure. Question is, does it need gradual heating to break in or set the rockers? No, these things are needle bearing pivots, and then everything else is polished finish. So I'm going to say no. When we put these together, this would be drenched in assembly lube. So push rods into the lifters, the rockers onto the push rods, and the rockers onto the valves. All that's coated with assembly lube. And as soon as you fire this engine up, it's wet, it's lubricated, and there's no extra braking on the rockers at all now. Now Teresa's getting ready to install some of the high pressure fuel piping on top of the engine. This carries the 2900 psi fuel up to that, over to the individual fuel rails. Now these joints on the end are special. They're a spherical joint with some lubricant on the back. And there's basically a lot of things engineered into this to make sure this is a joint that will go together and will not leak. After we fasten all these, we have a special tool that tightens up these tube nuts on here. In this case, there's a special tool. The actual one's a lot more impressive. It's an electronic Crowfoot wrench, wireless, so it's not connected to anything like this other one is. But we tighten those to 26 millimeters twice to make sure they're seated. And then we do what's called a helium leak test. We hook up something similar to an air conditioning evacuator where you basically pull a vacuum on the entire fuel system. We have 4 fingers that come down, basically long things with seals on the end. They grab around each of these fittings, pump helium, we surround those fittings with helium, and then monitor for helium molecules in the vacuum side. So every single engine gets that. And basically the tolerance on that is 0. If we see any helium in there, that comes back apart. Usually put a new one on.
Backing up a little bit, first 100 miles, where does that sacrificial coating wind up going?
That's a good question. The question is the sacrificial coating on the supercharger rotors, as you're wearing that in, where does the coating go? It's not it's more of a Teflon, it's a soft material, so it ends up it goes through the engine and it's blown out the exhaust. Tiny little particles. Actually, this is an improvement on the LS9. The LS9 supercharger had a different, this is more like Teflon. It was more like, electrodeposited metal is the right word, but it was a harder compound. It took a couple thousand miles to wear it. So, your supercharger would not be as quiet as it's going to get for maybe a couple thousand miles on the LS9. You guys gotta snuff those valve covers in on me. After the high pressure fuel rails go on, they put the rocker covers on. Same as the Gen 4, the coils are integrated into the rocker cover. There's some extra PCV outlets on these, but other than that, they're not a whole lot different than the valve covers have been for quite a while.
Yes.
I have never been building motors. I'm a quality engineer, but I've been with the PVC. The question was, how long have we all been building motors? Pedro and Teresa were the very first, among the very first group of Bowling Green employees that got involved in this project. Gentleman over there in the black sweatshirt, Barry, you probably know him. He was one of our original employees from Wixom. And he was up there back in 07, 08 time frame. And then he came down with this project. So Teresa and Pedro here got started, it was late 2013. First started traveling up a lot and spent months up in Wixom learning how to build from the guys that had been doing up there for 5-6 years. And they became our master trainers for, as we brought new people on, they were our main resource to train the new employees. So aside from Barry, there's another guy named Mike Priest, which if anybody has a Wixom engine, he'll build a lot of those. And then Rob Nichols is the manufacturing engineer. He's the guy that administers like all the torque tools and a lot of the leak testing equipment and things that we're talking about. He's in charge of all that. Those 3 people are the only ones that came down from Wixom. The other 23 builders, myself, and the production manager all are Bowling Green people. Yeah, I was just getting ready to talk about this. I hate using the word diesel when I talk about this, but this high pressure fuel pump is made by Standardine. They made an awful lot of diesels up throughout the years, so same technology goes into this. Of course, the same noise, similar kind of noise comes out of this system as would a high pressure injection in a diesel. So this, basically this fills every last crevice between the top of the engine and the bottom of the supercharger with this, keep that noise down. All those high pressure fuel pulses, they make a lot of vibration. Teresa's making some of the electrical connections that control the AFM, coolant temperature sensor, and a connector that goes onto the main engine wiring harness. Yes, sir. Oh, AFM, that was, for those of you that missed it earlier, active fuel management. That's just another shorthand for saying the 4-cylinder motor. So. Supercharger weighs somewhere around 60 pounds. We would normally have an overhead lift with a hook apparatus on the bottom that allows one person to move that over there and get it straight down onto the engine. This is a 1.7 liter supercharger. Spins up to 20,000 RPMs at max output at red line, and gives 9.4 pounds of boost at most. There is some hardware in the front here. It's kind of neat. This is the bypass valve. So I'm not going to advise anybody to change this or modify this, but when the engine's running with high vacuum, it pulls it open like this. So basically all the boost just goes right back into the intake and circulates. So you have less parasitic drag on the engine that way when you're in cruising mode. Then when you need close to the wide open door, part throttle, and you're loading the engine, this will close. So the boost is all going into right down into the engine. I didn't point it out, this thing's hard to tilt, but those of you who walked up and looked at this earlier, there are 2 intercooler, small radiators built in the top of this. Sure, it turns sideways. There is a separate coolant loop in Z06, separate from the engine coolant. It has Dex Cool in it, but it has its own little pump, has its own little radiator in front of the normal car radiator. Circulates water in these, into this manifold, goes through this system here. So basically as the air comes out of the supercharger sucks in here, blows out here, and we have a lid over this. So basically the air is forced back down through these to cool it back off. And that gives you a denser charge into your cylinder, more area, more power. But that comes to us assembled just like that.
Question.
Yes, sir.
So you get about 200 horsepower more out of the Z06 engine. Is that all coming from the supercharger or the mechanical member?
Question is, if you get 200 extra horsepower out of this engine compared to the LT1, same displacement. Question is, does that come from the supercharger or any other improvements? Short answer is yes, it's all from the supercharger. Actually, some of the the valve, like the camshaft durations and things, are even, like if you didn't have the supercharger, this engine would probably be weaker than the base engine, just because of the valve timing and things like that. They're engineered for a supercharger. So, short answer, yes, it's all from the supercharger. Now, there are some components in there for durability that hold together better at 650 horse than it would on the base engine. This is another one of our mandatory sequences. Something tells me you're not quite following it. I think we're starting the bolts here. But I don't want to steal you guys' thunder there. But actually, Pedro is following the sequence, isn't it? But there's a pictorial that hangs on this line, but I don't know, Pedro, after how many? A couple hundred? You probably do it in his sleep, I'm sure. Yes, sir.
From a quality control point of view, how do you ensure that all of those bolts are torqued to the right?
That's a good question. From a quality control point of view, how do we ensure all those bolts are torqued down? This controller here is, when you came in late. For those who came in late, for every fastener, we scan a barcode in this book. Well, actually, one of these sheets is at each station. So for the supercharger cover, scan that barcode right there, and that tells this controller to put out all the new meters to look for 20 good hits. So if it doesn't see 20, it's not going to allow Pedro to go on to the next fastener. And it will. This is their key actually. When you get they call this the flat line. When it sees all the rundowns it's looking for, it'll go here to tell you you're good, and you can move on. Yes, sir.
Loma video shows a smart bolt in the block.
Yes.
Used to rate RFID block. That gives us
The question is, do we use the RFID bolt that Tonawanda uses to track the engine through their system? Their system's it's huge. They have thousands of engines circulating in all different areas of their plant. So, short answer is no, we don't. We don't need it. We have a very simple system actually, and being simple, it's very flexible for us. We have a paper manifest that's attached to the engine. Wherever this is a unique ID, so it has a unique serial number with that GCN suffix there. Down below, there's a unique identification. That's the engine serial number right there. So whenever this engine comes into a station, we scan that, and that tells it what engine's there and what torques it needs to put out. When we go to our testing, cold testing and the balance, those also scan that, so they have a record that they tested that engine. And we basically cannot ship an engine that didn't get all the tests and didn't get all the torques, so it won't allow. The automated system won't allow us to ship that engine out. But obviously, if we were building 500 a shift on 3 shifts, we'd be using the RFID bolt for sure. Yes, sir. How many parts go in one complete engine? That's sort of the look. If you don't count bolts, well, yeah, we get, like, for example, we get pistons and rods in. Pistons on the rod has all the rings assembled, has the bolts in the assembly. So there's probably at least 10 parts right there. That's hard. That's a really good question. I wish I had the answer to that. That would be a nice, I'll tell you. I'll bet it's a couple hundred. I do know we have 56 different torques that we use. There's all the torques right there. It fits on the front and back of one page, so that's not too bad. Well, I guess it's different for everyone. Like the Supercharger comes out of South Carolina, Columbia, and then Heads and Block come out of Tonawanda, New York. It's Eaton. It's an Eaton Supercharger. Yep. They have done, I believe, all of GM Superchargers, at least for North America, for going back to the 3.8. Well, I guess it's not a really long list. 3.8, the 2.0 Cobalt SS engine, and then LS9, of course. That's right, there you go. I knew there was another North Star for the CTS, or the XLRV, and the, your car, right, the CSV. Right now, Teresa's installing a knock sensor. There's a knock sensor on each side of the engine that looks for detonation. Of course, in the supercharged engine, that's important. This engine calls for premium fuel. However, if you use 87 octane, it won't destroy the engine. The knock sensor will pick up the detonation, it'll cut timing, and you'll end up with less output. You won't get 650 horsepower on 87 octane, but it basically makes the engine drivable. Every modern engine has a knock sensor, so it's extra important on this one though. Gosh, you guys, I was running my track there, and you guys slipped the balancer on me. This is a unique crank pulley harmonic balancer for the LT4. It's aluminum, where it's steel on the other engines. So this is one of the unique parts for the LT4. That bolt in the center, that is, remember the cam phaser bolt was one of the highest. This is the highest. This one's up in the 300s usually. It's another torque angle fastener, but the final torque is usually a 350 range. Right now they're putting the exhaust manifolds on. There's a steel gasket there, and the manifolds are a cast stainless steel, so they're never going to rust, and they are a pretty good high flow design for a cast manifold. The bolts on those are a special design bolt. It's a trilobular bolt, which means the bolt isn't round. It's actually shaped like a triangle. So when it goes in, it actually cuts a little bit of its own thread, and it basically binds in the hole, making it so that it's less likely, basically it's never going to back out. It's almost like a locking feature.
Question.
Yes?
I've got a G51, and mine's much rougher as far as the header goes. Different material, mine's is raw cast iron.
Which part's rougher?
Cast iron.
See, on the LT1, the exhaust manifold's quite a bit rougher.
Mine rust all the time.
Well, those are cast iron
Yeah.
on the LT1, yeah. And I don't know if it's a different, I couldn't tell you if it's a different casting process or not. I do know the material is different, for sure. It's not a bad looking casting, you're right. So it's pretty smooth as they go. getting towards the end of the process here that we're going to show today. They're putting these spark plug wires on. We have multiple checks on spark plug wires to make sure those are on all the way when they leave us. These heat shields go on one of our last stages in the process. And then one thing we're not going to show today is the flywheel or flex plate installation. If you get an automatic, we make two different engines. We make a GCM and a GCN. GCM, strangely enough, is an automatic, and GCN is a manual. So if you were to order an automatic Z06, this would go on the, we dismount the engine from the cart here and we put it on a special stand to put the flywheel on, or I'm sorry, the flex plate. And in the case of the manual, we would get a flywheel and clutch. Show them the dual mass clutch here, Adrian. Or the dual mass flywheel, sorry. This is we call it a dual mass because you've got basically two separate pieces of this that rotate independently. And part of that is to soak up the driveline vibration you get. So this is pretty, this is a step up from the Gen 4s. We didn't have that on.
And it's a
The longer stands than ever gets. And we also have a dual clutch, which has two. I'm just going to show one. Basically, you've got one of these you can see, which is your normal clutch disc, and then being a dual clutch, there's another, the other side of the pressure plate there. You've got another friction disc in there, so they're geared together. So you've got a dual clutch there, so super, pretty high capacity clutch, higher than a normal single disc clutch. As mentioned earlier, after we would put the flywheel on, this engine would go over to cold test, where we spin it, basically check all the internal functions, look for all the right pressures and vacuums on the intake side and pressures on the exhaust side. And then if you had a manual engine, it would go over to get a final balance, where we are putting in the flywheel. We have these holes around the edge. We just have little steel hammer-in weights that we put in there to get right down to the final balance on that, and a little smaller weight we put in the front of the balancer there. So make that engine as smooth as possible on manuals, just to reduce the vibration in the shift handle, basically. And the rest of the driveline, of course, with the Corvette, with the torque tube, turning at engine speed, extra sensitive to vibration. Well, all I've got left now is the heat shields and spark plug wires on this side. This is pretty much the end of our demonstration. Anybody have any questions or anything I forgot to cover, want to ask about? All right, well, we're just going to button this up here, and feel free to walk up and look at it and touch, or we'll stay around here a little while longer and answer any questions or any questions you have about the PVC or Corvette in general. Thanks.